In this lesson, we will cover the basic counting rule or counting principle, permutations, combinations, as well as more on probabilities. Let's begin with the basic counting rule. If you are asked to choose one item from each of two separate categories, where there are m items in the first category and n items in the second category, then the total number of available choices is m times n. This is sometimes called the multiplication rule for probabilities. Let's look at an example. A gate code has a standard keypad with the digits 0 through 9. How many possible code combinations are there if the code is 4 digits long? So we can think of the 4 digits as 4 categories. So let's go ahead and model this. We have 1, 2, 3, 4 categories. For part A, repetition of the numbers is allowed, which means for each category, we can select any of the 0 through 9 digits, which means there are 10 choices. So because there are 10 choices for the first digit, 10 choices for the second digit, 10 choices for the third digit, and 10 choices for the fourth digit, the number of 4-digit codes when repetition is allowed is equal to 10 to the fourth, or a 1 with 4 zeros, giving us 10,000. There are 10,000 possible code combinations using 4 digits with repetition. For part B, it says repetition is not allowed. So again, using the counting principle or counting rule, we still have 4 categories. The first digit or first number can be any of the 10 choices. So there's 10 choices for the first digit in the code, but we cannot use this same digit again. So now there's only 9 choices for the second digit, 8 choices for the third digit, and 7 choices for the fourth digit. Notice how the number of choices decreases by 1 each time because repetition is not allowed. 10 times 9 times 8 times 7 is equal to 5,040. So when repetition is not allowed, there would be 5,040 code combinations. And now let's talk about factorials. N factorial is defined as n times n minus 1 times n minus 2 all the way down to times 3 times 2 times 1. So for example, 3 factorial is equal to 3 times 2 times 1, which is equal to 6. 5 factorial is equal to 5 times 4 times 3 times 2 times 1, which is equal to 120. We will check this on the T84 in just a moment, and by definition, 0 factorial is equal to 1. Let's check 5 factorial on the calculator. To do this, we press 5, math, right arrow to probability, and notice how factorial is option 4, so we press 4 and then enter. And now let's talk about permutations. We say there are n permute r permutations of size r that may be selected from among n choices without replacement when order matters. So it's important to remember when we talk about permutations, we do not have replacement and order does matter. And we say n permute r. N permute r is equal to n factorial divided by the quantity n minus r factorial. Let's take a look at some examples. How many ways can 8 athletes be awarded first, second, and third place? Well, here the order matters because the order indicates whether the athlete gets first, second, or third place. And of course, there's no repetition because if an athlete gets first, the athlete cannot get second or third place, and so on. One way to determine how many ways 8 athletes can be awarded first, second, and third place would be to determine 8 permute 3. Notice n is equal to 8, r is equal to 3, which gives us 8 factorial divided by n minus r factorial, which is 8 minus 3 factorial, which is equal to 8 factorial divided by 5 factorial. Simplifying, we have 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, all divided by 5 factorial, which is 5 times 4 times 3 times 2 times 1. Simplifying, 5 divided by 5 simplifies to 1, and so does 4 divided by 4, 3 divided by 3, 2 divided by 2 and 1 divided by 1. We're left with 8 times 7 times 6, which is equal to 336, giving us 336 ways. Now I do want to mention, we could have also solved this using the counting principle or counting rule, where there are 3 categories, first, second, and third. There would be 8 choices for first place, 7 choices for second place, and 6 choices for third place, giving us the same result of 336. Let's also show how to evaluate a permutation on the TI-84. We enter n, which is 8, math, right arrow to probability. Notice permutation is option 2, so we press 2, enter r, which is 3, and enter, which of course gives us the same result. For 13, how many ways can 5 friends line up to buy tickets? Here order matters, and we do not have repetition, and therefore we can solve this using a permutation. All 5 friends are lining up, and therefore it would be 5 permute 5. Using our permutation definition, we have 5 factorial divided by n minus r factorial, which would be 5 minus 5 factorial, which gives us 5 factorial over 0 factorial. But 0 factorial is equal to 1, and therefore we just have 5 times 4 times 3 times 2 times 1 over 1, which is equal to 120. We saw this earlier. So there are 120 ways 5 friends can line up to buy tickets. Or again, using the counting principle, there would be 5 categories or 5 slots, 5 choices for the first position, 4 choices for the second, 3 choices for the third, 2 choices for the fourth, and 1 choice for the fifth, giving us the same result as 120. Number 14, how many 3-letter words can be made from 5 letters, F, G, H, I, J, if repetition of the letters first is allowed and then is not allowed? So if repetition is allowed, we cannot use a permutation. We have to use the counting principle or counting rule, where there would be 3 categories because we are forming 3-letter words. So 1, 2, 3. Again, repetition is allowed, and there are 5 letters. There are 5 choices for each of the 3 letters. So 5 times 5 times 5 is equal to 5 cubed, which is equal to 125. There would be 125 possible 3-letter words. For part B, repetition is not allowed. So because there's no repetition and order matters, we could use a permutation or the counting principle or counting rule. Let's first use the counting principle or counting rule, where there will be 3 positions. Because repetition is not allowed, there's 5 choices for the first letter, 4 choices for the second letter, and 3 choices for the third letter. 5 times 4 times 3 is equal to 60. There are 60 possible 3-letter words if repetition is not allowed. Or using a permutation, we could have done 5 permute 3, which is equal to 5 factorial over 5 minus 3 factorial, which is equal to 5 factorial divided by 2 factorial. Simplifying by hand, we'd have 5 times 4 times 3 times 2 times 1 is 2 factorial, divided by 2 factorial. 2 factorial divided by itself simplifies to 1, of course leaving us with 5 times 4 times 3, which is also 60. And now let's talk about combinations. We say there are n choose 4 combinations of size r that can be selected from n choices without replacement when order does not matter. So for combinations, order does not matter. Remember, for permutations, order does matter. And in both cases, we do not have replacement. So we say n choose r is equal to n factorial divided by the product of n minus r factorial and r factorial. Let's look at some examples. So for number 15, in a lottery daily game, a player picks 3 numbers from 0 to 9 without repetition. How many different choices does the player have? for part A, if the order matters. So again, if the order matters, we have a permutation. There are 10 digits, and the player is selecting 3 of them. So if order does matter, the number of ways would be 10 permute 3, which is equal to 10 factorial divided by 10 minus 3 factorial, which is equal to 10 factorial divided by 7 factorial. By hand, we have 10 times 9 times 8. The remaining factors would be 7 factorial divided by 7 factorial. Simplifying, 10 times 9 times 8 is equal to 720. There are 720 ways to select 3 numbers from 0 to 9 if order matters. Let's check this on the T84. We have 10, math, right arrow to probability, option 2 for permutation, 3 enter, which verifies the results. We could have also used the counting principle, where there are 3 categories, 10 choices for the first, 9 choices for the second, 8 choices for the third, giving us the same result of 720. For part B, we're now told the order does not matter. Because the order does not matter, we have to use a combination. We cannot use a permutation or the counting principle. So because the order does not matter, we would have 10 choose 3, which is equal to 10 factorial divided by the product of n minus r factorial and r factorial, which would give us 10 minus 3 factorial times 3 factorial. Simplifying by hand, we have 10 factorial over 7 factorial, 3 factorial. 10 factorial is equal to 10 times 9 times 8. I'll stop here. The remaining factors would be 7 factorial divided by 7 factorial. So this is going to simplify. 3 factorial is 3 times 2 times 1. Simplifying, 7 factorial divided by itself simplifies to 1. From here, 3 and 9 simplify. There's 1, 3, and 3, 3 3s and 9. 2 and 8 simplify. There's 1, 2, and 2, and 4 2s and 8. We're left with 10 times 3 times 4, which is 120. There are 120 ways to pick 3 numbers from 0 to 9 if order does not matter. And again, let's verify this on the 84. We have 10, math, right arrow to probability, option 3 for combination, R is 3, enter, which gives us 120. Okay, so for number 16 now, how many different 5-card hands can be dealt from a deck of 52 cards? The order of the cards does not matter in this case. We are dealing 5 cards from 52. We do not have replacement, and order does not matter, and therefore we'd have 52 choose 5, which would be 52 factorial divided by the product of 52 minus 5 factorial times 5 factorial. Let's just evaluate this on the T84. So we have 52 math, right arrow to probability. Combination is option 3. R is 5, enter. We have 2,598,960 ways. And now for our last example, we'll be using combinations as well as the counting principle to determine probabilities. A poker hand consists of 5 cards randomly dealt from a standard deck of 52 cards. The order of the cards does not matter. Determine the following probabilities for a 5-card poker hand. Write your answers in percent form, rounded to 4 decimal places. For part A, we want to determine the probability that exactly 4 of the cards are aces. We need to be careful here because it's a 5-card hand. This is really the probability of 4 aces and 1 non-ace. Let's begin with the denominator, which is the number of ways 5-card hands can be dealt from 52 cards, which should be 52 choose 5. And now for the numerator, we want to find the number of ways 4 aces can be dealt and 1 non-ace. Well, the number of ways 4 aces can be chosen is 4 choose 4, because there are 4 aces and you're choosing all 4 of them. And then we have times the number of ways of selecting one non-ace or choosing one non-ace. There are 48 cards that are not aces. The number of ways of selecting one non-ace is 48, choose 1. And now to evaluate this on the TI-84. We do need the numerator in parentheses. We have open parenthesis for math, probability, option 3 for combination, 4, right arrow, times 48, math, probability, combination, which is 3, R is 1, right arrow, close parenthesis, divided by 52, choose 5. Now notice here we're getting scientific notation. This e negative 5 means times 10 to the power of negative 5. To convert to a decimal, we have to move the decimal point 5 places to the left, which would be 0.000018 rounded to 6 decimal places. But let's first write this as 1.8 times 10 to the power of negative 5. And for review, to convert to decimal notation, we move the decimal 5 places to the left. So 1, 2, 3, 4, 5. Fill in the missing digits with zeros, which gives us 0.000018, which is the percentage, is 0.0018%. Notice how it's very unlikely you would get 4 aces in a 5-card poker hand. Letter B is more straightforward. Determine the probability that all 5 of the cards are spades. There are 13 spades in the deck, so the probability of drawing 5 spades, beginning with the denominator, would be 52, choose 5. And the number of ways of selecting 5 spades from 13 spades is 13, choose 5. Going back to the calculator, we have 13 choose 5, right arrow, divided by 52, choose 5. Again, we have scientific notation, but now we have e negative 4, which means times 10 to the power of negative 4. We need to move the decimal point 4 places to the left, which would give us 0.000495 to 6 decimal places. But let's first write 4.95 times 10 to the power of negative 4, which is equal to 0.000495, which is the percentage, is 0.0495%. For part C, determine the probability of selecting exactly 2 aces and exactly 2 kings, which means the 5th card cannot be an ace and cannot be a king. Beginning with the denominator, we have 52, choose 5 because we have a 5-card hand. The number of ways of selecting 2 aces would be 4, choose 2 because there are 4 aces in the deck. So 4, choose 2 is the number of ways of selecting 2 aces times the number of ways of selecting 2 kings from 4 kings, that'd be 4, choose 2, times the 5th card can be any card except it cannot be an ace and it also cannot be a king. Well, there are 4 aces and 4 kings. 52 minus 8 is equal to 44. There are 44 cards that would not be an ace and not be a king. The number of ways of selecting one card that's not an ace and not a king would be 44, choose 1. Going back to the calculator one last time. Open parenthesis, 4, choose 2. Right arrow, times 4, choose 2 again. Right arrow, times 44, choose 1. Right arrow, close parenthesis, divided by 52, choose 5. Again, we have scientific notation. e negative 4 means times 10 to the power of negative 4. To 6 decimal places, we have 0.000609. Let's begin with 6.09 times 10 to the power of negative 4, which is equal to 0.000609, which is a percentage, would be 0.0609%. Okay, I hope you found this helpful.